Well, good morning. Like the other presenter said, thank you for joining this Wednesday morning session. My name is Marisol Tsui-Chang, and I'm a senior project engineer for Olson Engineering. And today I will be talking about case studies of data fusion of non-destructive testing and photogrammetry for concrete condition imaging and assessment. So I'm going to start with a little introduction. I'll discuss a little bit about what photogrammetry and NDE data fusion is. And then I'll present on two case studies, one for fusion overlay of NDE scanning and photogrammetric image results for concrete bridge girders, and the second one for a new concrete shear wall. And then I'll finalize with my summary and conclusions. So, as we may know, visual inspection is typically the first step in most concrete condition assessment studies. Engineers and inspectors will manually record condition maps and sketches, and then take selected photos of specific defects or anomalies. However, for complex projects where you do have a lot of anomalies on the surface, as you can see in the examples above, crack maps are just not enough. They're very confusing, and again, you only really take selected photographs of the most important, let's say, defects. A complementary tool that can be used for this particular limitation is photogrammetry. So what is photogrammetry? Photogrammetry is the science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring, and interpreting photographic images and patterns of electromagnetic radiant imagery and other phenomena. So, essentially, the photogrammetric method uses motion algorithms to create a 3D model from overlapping images. Typically, the photogrammetry steps start with capturing digital images with a high-resolution camera. In this case, if you look in your pockets, you'll see that your high-resolution camera is right there on your phone. You then continue with identifying and repeating target features within photographs. And then you use the angle changes in these target features between photo to photo to determine a 3D structure of your object. Then you project the pixels of the digital images on the 3D structure and generate texture around these pixels. And finally, as an additional step, if you are dealing with a planar surface, such as a slab, wall, rectangular columns, that sort of thing, you can then create an orthomosaic image, which is a 2D render of the 3D polygonal mesh model. For us folks at Olson, we use AGI soft metashape for the image processing on a Windows PC with a fast processor. And typically for high-resolution images, it takes about 1 to 2 hours to process. And again, obviously, this depends on the size of your object or surface. Some of the advantages of this method are, first, that it's a low cost in equipment. Again, you can use your phone camera or an economical point-and-click camera. This method can be used to monitor surface deterioration progress over time, and it can provide detailed permanent records of defects marked during the inspection. And again, with this, depending on the camera and how close you are and how many photographs you take, it can really create high-resolution images of your structures and areas. Some of the limitations include that you can only collect data on objects in line of sight, so you do need access to these particular areas that you're accessing. You do need reference features, multiple angles, and good overlap between the photographs for full coverage. And again, you can start dealing with very large data files, which then brings up the issue of data storage and management. So how does it integrate with non-destructive evaluation? Data fusion is the synthesis of photogrammetry and NDE data, where the implementation of data fusion can link the surface defects from photogrammetry and subsurface conditions and anomalies from non-destructive evaluation to ultimately produce an integrated multi-method visual and NDE work product. Recently, data fusion has been increasingly adopted by engineers and owners to achieve a more complete concrete condition assessment. So the first case study I'll be talking about is a fusion overlay of NDE scanning and photogrammetric image results for concrete bridge girders. A little background on this project. This was a bridge built in the 1970s. Due to its location, it does have both marine and de-icing salt exposure. The areas we were interested in were these Corbel joints at the ends of this longest center drop-in span. So if you imagine two piers and two cantilever spans, there was the drop-in span in the middle, and so the Corbel joints at the end of this drop-in span were the areas that we were interested in. We had about, I believe, 11 Corbel joints per pier, so 22 Corbel joints total. As you can see from these photographs, we had fairly limited access. You can really only access these Corbel joints for the inspection and everything with a UV or a man lift on a barge that you had to get out there every morning and work over water, obviously. As you can see from this photograph in the middle, the left side is that cantilever span, and then the right side is where that drop-in span comes down on it, and there's a diaphragm perpendicular to the girders. And again, as you can see on the right, these were girders that had around 6 PT ducts based on the plans. Visual inspection revealed extensive cracking and delamination. Localized repairs were performed in 2010, and then they just kept monitoring it thereafter. So the project objectives were to determine the existing layout of reinforcement and identify a key structural metal embedment plate and the PT duct components, and we used ground penetrating radar for this. The second objective was to assess the condition of the post-tension duct grout with impact echo scanning. And the third was to assess the overall concrete condition with impact echo scanning and spectral analysis of surface waves. So this is a fully processed orthomosaic image of one of the Corbel joints. You can see on the left, that's where that cantilever span is, and on the right, that's where the drop-in span is. The white area in the middle is kind of where the diaphragm should be coming in and out of the page, which we took out because it was too confusing. You can see in the surface the marks that the inspection team marked out beforehand were the blue areas with an H were marked for hollow for the sounding that they were doing in previous years. And then the little dots on the left you can see were visible cracks that they were trying to map out. The little crosses, the red crosses, were put there for us for our testing, and they are a 6-inch grid. And for this fully processed orthomosaic image, it took us about 150 to 250 photos, and we took those within 10 minutes of each other, in a period of 10 minutes. There was a 50% horizontal overlap and 30% vertical overlap between the discrete images. They were fairly leveled in angle and consistent from a consistent distance from the surface, and they were all taken consecutively so as to avoid any light changes that may distort the image processing. For the ground penetrating radar, we used a GSSI structure scan mini XT unit with a 2700 megahertz antenna. We did both vertical and horizontal scans on a 3-inch grid for 3D GPR data analysis. We analyzed the radar data by first looking at the unprocessed B scan and identifying the hyperbola reflections for both the rebar and the ducts. The signals were then migrated to collapse the hyperbola reflections from the rebar and ducts to their locations. The pulses were then merged into a single pulse envelope via Hilbert transform, and the transform data is then gridded in the 2 directions and summed, and the tendons and the rebars were then noted on the data. So this is an example result of the 3D GPR with multiple depth slices at different locations overlaid on that orthomosaic, where you can see on the left and on the right, on the leftmost and rightmost, the tendons over there. You can see in the middle on the depth slices, the vertical, horizontal, and diagonal reinforcement, as well as the embedded plates that the client was really interested in identifying. And again, these results were overlaid on that respective orthomosaic, so if the client wanted to go back and destructively confirm locations of the plates, for example, they can easily do that with these results. For the impact echo scanning, we use an Olson Instruments Freedom Data PC, an Olson IES scanner with an integrated solenoid impactor. And we only performed vertical lines because we wanted to cross those ducts, and we did those at every 6 inches along the girders. So these are IES example results for both grouted versus voided ducts. On the left, you can see a scan line of thickness versus the scan distance, where you can see a very consistent 7.5-inch echo thickness. Again, these were crossing known ducts, so the fact that there is no change in that thickness gives us good confidence that the ducts were well grouted. On the right side, you can see an example result for poor voided duct grouting conditions, noted by that increase in the thickness shown between 3.5 and 4.2 feet. And that increase in thickness has been generally attributed to the reduction in velocity from the condition of the grout material in the ducts, also the size of the ducts and the material of the duct itself. So when we put everything together, all those lines together, when we plot them over the orthomosaic, we can see these increases in the apparent thickness, in this case marked in blues, like light blue and dark blue. And these generally correlated well within each line. You can see that increase in each line, and they align very well with where we thought that the ducts were based on the GDPR. Overall, in this particular example, we can see that the ducts on the left web, specifically the top 3 ducts, were the ones that were showing questionable or poor grout conditions, compared to the right side of the top web, where you could see that it was consistently sound concrete. For the spectral analysis of surface waves, we tested only across visible cracks. We used an Olson Instruments Freedom Data PC, an SASW bar with 2 displacement transducers, and the bar was spaced 1.31 feet, which gives you a depth range between 3 to 40 inches. And we used a 2-ounce metal mopping hammer for inline impacts. So these are some of the SASW results, where on the left side you can see an example dispersion curve of sound conditions, where this location was 7.5 inches thick. So we can see a 7,000 feet per second velocity from 4 inches to 7.5 inches, and there's a big drop in that velocity, which corresponds to the back side of that section. On the right side, we see an example result for an SASW across a crack, indicating low velocities and then an inflection point where that velocity starts to increase, and that's typically correlated with the crack tip. As if you think about it as velocity and depth, there is good material past that tip. That's why the increase. That's why there's an increase in the velocity. So when you put everything together, the IES and the SASW over the orthomosaic, this is the end result, where you can see the marked out areas in blue from the inspection team, from that sounding that I showed you at the beginning, and the apparent thickness from the impact echo that was divided into categories based on what we knew from the plans. Divided into specific types of defects, such as shallow delaminations, deep delaminations, or defects around the PT ducts. And as you can see from the area right underneath that seat, the impact echo results correlated well with the sounding from the inspectors. We were able to find a couple more areas that did have other issues that they didn't sound or they didn't catch. The limited SASW performed, you can see from the little dots, we categorized them based on crack tip depth with different colors, and then we overlaid them over exactly where these tests were done. So now the crack tip depth can be integrally presented over the specific cracks tested. So you don't have to go fumble around, figure out what was what or what you tested. The second case study that I'm going to be presenting is fusion overlay of NDE scanning and photogrammetric image results for a new concrete shear wall. So this was a little different. This wall consisted of 2 walls and 3 boundary members. It was newly built in 2021. the geometries of the walls and boundary members you can see on the screen. And essentially this was a self-consolidated concrete shear wall that due to delays in the concrete placement, once they took out the formwork, they saw all these visible lift lines on the surface. In this case, lift lines would be defined as the surface lines between layers of poured concrete. And because it was new construction, we were working mostly with the quality team to provide NDE for repair plans for these lift lines. The project objectives were to verify the lift lines coincided with the horizontal reinforcements, and we used ground penetrating radar for this. The second one was to locate any significant internal honeycomb or void conditions within the wall. We used impact echo for this. And the third was to determine the depth, width, and extent of separation or honeycomb conditions at visible lift lines, and we used spectral analysis of surface waves for this. So again, this is the fully processed orthomosaic image from photogrammetry. You can kind of see, I couldn't fit it all very well, but if you zoom in, you can see the lift lines kind of running along. There are many, and they're all throughout. For this particular ortho, we took 1,700 photos total, taken within a span of 30 minutes. And it was 30 minutes because we had to use a scissor lift to be able to access the top area. So then you have to move the lift and everything. Again, we used 50% horizontal overlap and 30% vertical overlap between these discrete images. The images were fairly leveled in angle and consistent distance from the surface, and obviously taken consecutively again to avoid those slight changes. So for the ground penetrating radar, we used again a GSSI structure scan mini C unit with a 2700 megahertz antenna. And since our only objective was to determine whether the lift lines coincided with longitudinal reinforcement, we only performed vertical scans, and we marked on site essentially with a blue crayon. Then that later was accentuated by in the office by the blue lines that you can see over here. And overall, these results show that most lift lines did align well with the reinforcement location, which is something the client wanted to know. For the impact echo testing, again, we used the Olson Instruments Freedom Data PC. Because we did point by point, we used an IE1 test head and a 2-ounce ball peen hammer as an impact source. And we did a 2-foot grid along the across the entire wall. So these are the impact echo results over the orthomosaic. The impact echo was analyzed by using the known thickness at each location and then back calculating an IE velocity. These IE velocities at each point were then compared to a calibrated velocity from a shear wall nearby that had the same mix. And the IE condition rating for every single point was compared by different percent velocity reductions, where sound was within 10%, questionable was between 10 and 20%, and poor was 20% or more velocity reduction. And as you can see here, the majority of the points were, if almost all, were sound conditions, which was good news for our client, and it also indicated that they didn't have extensive issues within the wall. Oh, and then the only point that they had that was questionable, because there was again overlaid over the orthomosaic, the client could go out there and destructively investigate what was going on with that particular point if they wanted to. And finally, the spectral analysis of surface waves. We tested only across the lift lines. We used an Olson Instruments Freedom Data PC and a bar with 2 displacement transducers. The bar was spaced at 0.59 feet, which gives you a depth range between 1.5 to 17 inches. And again, we used a 2-ounce small metal ball peen hammer for inline impacts. So these are the surface wave results over the photogrammetry over the orthomosaic, where the SASW data was analyzed again by, on the right side, the dispersion curve by looking for that inflection point where the velocity starts to increase, and that's what we call that as the lift line tip. The SASW condition ratings were again categorized based on the depth of that lift line, and then we plotted everything over the ortho so you could see exactly which were the lift lines that were deeper from the surface. This plot was very useful in being able to identify the areas with more severe lift lines And in planning a repair plan for this wall, these results served as a detailed map of spots that needed more attention or in general different repair procedures. So in summary, the process of data fusion combines discrete photos turned into a 3D model, turned into an orthomosaic image from photogrammetry with conventional NDE results to generate a geometrically correct, integrated multi-method visual and NDE work product. And I presented 2 case studies a little fast, I apologize, showing this process in detail. And in conclusion, data fusion can be a powerful tool that can link the internal anomalies from NDE inspection to surface defects from photogrammetry. It can be considered a low-cost method that can be used to monitor surface deterioration progress over time, and it can serve as a permanent inspection log as well. Other applications that we've seen in this particular use of photogrammetry is condition assessment and asset management of bridge decks, and using drones to access areas that are hard to access. Thank you.